I'm Daniele, a student at Sapienza, University of Rome, and today I'll talk about extensions of Petri nets, and in particular about nets with mana, which are an application of extensions of Petri nets to chemical reaction modeling. This talk originates from a paper, which is joint work with Fabrizio Genovese and Foscolo Reggian. And okay, last thing before starting is that I'd like to thank all the organizers of this wonderful event for well, organizing it in the first place. I had a blast. And yeah, also for giving me the opportunity of giving my first talk ever. So thanks, it means a lot to me. Okay, here you can see a Petri net modeling a chemical reaction which is called ATP hydrolysis. And Petri nets are actually pretty good at modeling chemical reactions, but they're not a perfect framework, and we'll see how to improve that. But first, let's talk a bit about the standard Petri net lingo. These round things are called places and represent types of resources. And places can hold these DALs, which are called tokens. And tokens just stand in for the amount of resources you have. So, for example, this ATP place has 2 tokens inside it. So we know that we have 2 molecules of ATP. And these square thingies are called transitions and represent processes that consume tokens and produce other tokens. But modeling chemical reactions and in general concurrent processes, because Petri nets are also quite good at modeling concurrent processes, isn't that easy. In fact, you need context quite often for things to happen. For example, you might need a chemical reaction to happen in the right temperature, or you might need a certain catalyst or enzyme to be present in your environment for your chemical reaction to happen. And the second thing is that processes don't run forever. And for example, machines wear out and stop working, or enzymes just lose their effectiveness with use. And that's why our bodies age and eventually die. And we'd like to take this into account into our models and use some cool category theory in the meantime. And well, we have devised 2 approaches. The first one is a naive internal way in which you functorially turn an old net, a Petri net, into another Petri net which has new places added for each transition, which act as a sort of a life bar for it. And we also have a cool external way in which we have a new flavor of Petri net, not just standard Petri nets, in which tokens can hold information about the state of the net. This information is non-local, but it can be joined into global information. And well, in this case, it's just about how many times a transition can run before just stopping to work. But you can extend it in other interesting ways. And the cool thing is that you can internalize this information and compile it back to a classic Petri net. And that's good because you can use all the well-established tools for Petri net analysis and model checking. Yeah, and this also has the advantage over the internal construction of being sort of type aware, because you actually distinguish from the chemical reaction layer to and the enzyme layer, the mana layer, as we'll call it. So before going over extensions of Petri nets, I'll have to tell you what a Petri net is. And a Petri net is just a set of places, a set of transitions, and 2 functions from the set of transition to the set of to the free commutative monoid on the set of places. These 2 functions are called source and target. And yeah, Just note that without the whole token dynamics thing, this is the same thing as a directed hypergraph. So we need to define markings on our nets. And a marking is just a function from P to the set of natural numbers, which stands in for a distribution of tokens in our places. And we'll say that a transition is enabled in a marking if this multiset difference is defined. And an enabled transition can fire in a marking and produce another marking via this formula. We can build a category of pattern nets, which has as its object pattern nets, and as morphisms, a pair of functions, one for the set of transitions and one for the set of places. That makes these two squares commute. And here Gn is just the lifting of G to multisets, or the free commutative monoid. And we can also build free commutative strict monoidal categories out of pattern nets. If you're confused about what commutative means, it's just like being symmetric monoidal, but in a really strict way. In fact, A tensor B, it's equal to B tensor A, and not just isomorphic. And we'll call this category we get out of a net. It's a category of executions, or CN. And this construction is quite similar to the free category on a directed graph, or its path category. And well, it has as its monoid of objects the free commutative monoid on P, and as its tensor product just the usual multiset sum operation. And for morphisms, you get a generator for each transition of your net, and you generate all the morphisms by taking all formal parallel and sequential compositions of generators and of identities. As you probably noticed, the objects in CN represent markings of our net, and morphisms represent executions, which are parallel and sequential firings of transitions. And this construction defines a functor from Petri to CSMC, which is the category of commutative strict monoidal categories and strict monoidal functors. And this functor has a right adjoint. Okay, now we can talk about the actual original part of this work, and we'll start with the internal mana construction, which is just another kind of free commutative strict monoidal category you can build out of a net. And in fact, the internal mana construction, or C mana n, will read this symbol as mana. This is a reference to Magic the Gathering. And yeah, it's just generated by this set, which is the co-product of P and T. And the generating morphisms are just the same as generating morphisms in CN, but for each one of the generating morphisms, you add another object to its domain, which represents the generator in CN. And by the adjunction between Petri and CSMC, we know that every FCSMC is presented by a net. So we just created a new net out of the net we were starting from, which for each transition has a new place added, which is called its mana place. And yeah, this assignment is functorial and defines a comonad on the category of free commutative strict monoidal categories and strict monoidal functors. Now for the external part, we'll need to talk about what a non-local commutative semantics is. And well, you just take a monoidal category M, and a net with non-local commutative M semantics, sorry if that's a mouthful, is just a pair of a net and a lax monoidal functor from its category of executions to M. And if you have two nets with non-local commutative M semantics, morphism between them is just a strict monoidal functor from their categories of executions that makes the obvious triangle commute. And for the external mana construction, we'll define it as a non-local commutative span semantics, in which span is one category and not a bicategory. It's just the category of sets and spans, in which isomorphic spans are quotiented out. And the action on objects of this functor is just mapping every object to this set, Tn, and each morphism is sent to this span, in which Fn is just a counter for generating morphisms used in F. And this is a lax monoidal functor, so it respects our definition of non-local commutative semantics. And in this setting, we have all the nice definitions of markings and findings. In fact, a marking in N in this stuff is just a pair of an object of Cn, which is a marking of the underlying net, and a multiset on T, a finite multiset on T, which is just a distribution of mana for each transition. So for a transition to be enabled in this framework, on top of being enabled in the underlying net, you also have to, you need for this multiset difference to be defined. And firing a transition just produces a marking which has one less mana. For example, in this picture, F has 1 mana, and upon firing, it consumes the only mana it had left. And even though it is still enabled in its underlying net, this transition, it cannot fire anymore because it has no mana left. And you can also internalize this by building its category of elements. So you take n sharp, the functor we just defined, our external mana construction, and you build the category of elements out of it. And this category is isomorphic to C mana n, and that's really nice, but it's also kind of restrictive because, which acts as a life bar for it. And what if we want more? It's time to talk about generalized mana constructions, and we'll start from the internal case. And a generalized internal mana construction for a given net is just a free commutative strict monoidal category that has as its generating objects the coproduct of P and T. And for each generating morphism in Cn, you have a generator in your generalized mana net that it's kind of the same, but it has an additional object in its domain and one in its codomain. The one in the domain, it's just a multiset with which contains only copies of U, the generator you're representing, and the one in the codomain is just a multiset on the set of transitions. Okay, by generalizing mana nets this way, we can now have a transition firing without consuming mana, like this one, and transitions that consume more than 1 mana to fire, or that produce mana upon firing, not only for themselves, but also for other mana places, like this transition here, and this one, and also this one. So we can model all kinds of interesting things. For example, catalysts, which have already been explored in category theory and pattern nets by John Baez and Joe Muller. And we can also model self-sustaining systems, which are pretty interesting if you read Life Itself by Rosen. So for the external construction, we'll need to relax our definition of non-local commutative semantics, and will allow not only lax monoidal functors to monoidal categories, but will allow lax monoidal lax functors to monoidal bicategories. Sorry if that's a mouthful, but that's just how it is. And we'll use...
Is everyone else having...
If you take...
Sorry, Daniele, you just cut out, your sound cut out for about 30 seconds there.
Oh, so
I think you were saying...
What was the last word you heard?
You said that's the way it is, though, I think.
Okay. So we'll use a really nice piece of mathematics, which is called the Grothendieck construction. And it tells us that if we have a category C, there is an equivalence between its slice and the category of lax functors from C to span. And in this case, span it's the usual bicategory. And the morphisms of this category are just lax natural transformations. And well, if we have a functor from D to C, we can get a lax functor from C to span, which we call gamma F, in this way, which I'm not going to read. And yeah, the other way around, if we have a lax functor from C to span, we can get a category, which we'll call the total category on F, and a functor, one functor, which we call the counit or the total functor on F, by just pulling this U back along F. And U is just the forgetful functor from the bicategory of pointed spans to the bicategory of spans, and this pullback is in the category of bicategories and lax functors. And moreover, our total category on F and the D from the previous slide are isomorphic. So this will allow us to build an external mana construction from an internal one. In fact, for each generalized mana net, we get a strict monoidal functor from C mana n to Cn, which sends each generator of Cn to itself and all the other junk into the monoidal unit, and sends each morphism generator to itself. And we can just plug this into the Grothendieck construction and get an external mana construction. In fact, monoidality of this functor implies that gamma F is lax monoidal lax functor. And that's everything I wanted to say about that. If you're interested about other kinds of extensions of pattern nets, we wrote a lot about this, and also we worked out all the above and also the mana net case in the symmetric monoidal case, which is pretty hard. But the Grothendieck construction is really useful for dealing with that. And we're also working on a lot of other applications of extensions of pattern nets to stuff that it's Turing complete. Pattern nets aren't a Turing complete model of computations, but timed nets, nets with inhibitor arcs, and history-dependent nets are, and we're working on it. Also, we're working on exporting this framework to graph extensions, And we're always on the lookout for new and interesting kinds of span semantics in general. So I'm done with my talk. Thanks for listening to it.
Thank you so much. Let's thank the speaker now. Unmute yourself if you like.